In this video, I'm going to discuss with you a couple of forces that are going to be important for this 9 weeks, and that is the force of friction and the normal force and the force of gravity. So we're going to start off with a flat surface, and then we're going to upgrade to an inclined surface. So on a flat surface, whenever you're given any object, whether it's a car, motorcycle, box, sphere, ball, the first thing you should always draw, the first force that you need to always draw is the force of gravity. And the force of gravity is always pointing downwards. And the force of gravity is calculated just like any other force is calculated by taking mass times acceleration. Because Newton's second law says F equals ma, where your force is in newtons, your mass is in kilograms, your acceleration is in meters per second squared. For the force of gravity, we are just substituting a little small g instead of an a, because that's the acceleration of gravity. It's such a specific acceleration that we use the letter g. However, you can go back to using a if you want to. But that's where your 9.8 meters per second squared or your 10 meters per second squared is going to go in. Your mass is going to be in kilograms, and your force of gravity is going to come out of newtons. Keep in mind one thing: your force of gravity is the same thing as your weight. This is a very important thing for you to remember. Your weight and your force of gravity are the same thing. That's why your weight changes when you switch planets. When you go from Earth to Mars, or when you go from Earth to the Moon, the force of gravity is weaker on the Moon, and the acceleration of gravity is weaker on the Moon, so your weight is going to be less on the Moon. Your mass will be the same, because you still have the same number of atoms, same molecules, you have the same mass when you go from planet to planet. Your mass won't change, but because the acceleration of gravity is changing based on the planet, your force of gravity is changing, thus your weight is changing. Now on a flat surface, the force of gravity is trying to push this box down into the surface. If the surface is strong enough, it prevents the box from going down, and it keeps the box in equilibrium. That means that the surface is exerting an equal and opposite force upwards. So the force of gravity is being countered by the force that the surface is exerting on the box. And the force that the surface exerts on the box is called the normal force. The normal force is the force that the surface exerts on the box in response to the force that the box is exerting on the surface, to keep the box in equilibrium. And the normal force is always perpendicular to the surface. The normal force is labeled as F subscript capital N. Some teachers label it as just capital N, so you should know both. In this case, these two forces are equal to each other, so the normal force is just as strong as the force of gravity. So if the force of gravity was 1,000 newtons, the normal force is 1,000 newtons. The other thing you want to keep in mind is that if you have a force pulling this object to the right, let's say we're pulling to the right with a force of 10 newtons, 15 newtons, 20 newtons, whatever force we're applying, pulling the object to the right, FA stands for applied force. If the box is not moving, if it won't move, well, that means there is a force of friction in the opposite direction. Now you have two types of force of friction. You have a static friction and you have a kinetic friction. Static friction is when an object is at rest, it's not moving. So to get the box to move, the force that you're applying has to be greater than the static friction to get the box to move, to accelerate it from 0 to a particular velocity. Once the box starts moving, and if you want to keep it moving at a constant speed, you have to exert a force that counters the force of kinetic friction, because when an object's at rest and you pull on it, then you're fighting against static friction. But once an object starts moving, then you're fighting against something called kinetic friction. Kinetic friction is weaker than static friction. Static friction is stronger than kinetic friction. The reason for that is because, if you go back to Newton's first law, an object at rest prefers to stay at rest unless a force acts upon it. And an object in motion prefers to stay in motion unless a force acts upon it. So it's tougher to move an object at rest than it is to keep an object moving. So static friction is greater than kinetic friction. When an object's at rest, the amount of friction between it and the surface is greater than when an object is moving. Remember, friction is a reactionary force. If the object is at rest and you aren't pulling on it, there is no applied force, then there's no friction. There will only be force of friction when you start pulling one way, then friction fights in the opposite direction. And remember, you have two types of friction. Static is when the object's at rest and you're trying to get it to move. Once you get it to move, then you switch from static friction to kinetic friction. Once an object's already moving, then you're fighting against kinetic friction, and kinetic friction is weaker than static friction. Now, also keep in mind, if you want an object to move at a constant speed, if the object is moving and you want to maintain its velocity, you want to make sure the velocity is at constant speed, then this force has to be just as strong as this force. Then the object won't accelerate, it will move at a constant speed. However, if you want the object to accelerate to the right, then it makes sense that this force has to be greater than this force. When this force is greater than this force, then the object will accelerate towards the right. And of course, vice versa, if this force is greater than this force, the object is going to slow down. It's going to have a negative acceleration. Some people call it a deceleration. So keep that in mind. When forces are equal and opposite, they cancel each other out, so the net force becomes 0, and there won't be any acceleration. So if this, once the box is moving, and you apply a force of 10 newtons to counter the force of friction, which is also 10 newtons, then the object will maintain a constant velocity. It won't accelerate. This force has to be greater than this force for the object to accelerate to the right. And if this force is greater than the applied force, the force of friction is greater than the applied force, then the object will slow down, and it's going to have a negative acceleration in the opposite direction. So this, in a nutshell, is an object that is on a flat surface. Now, if you had an inclined surface, angle theta, the diagram changes by a little bit. The force of gravity is still present. The force of gravity is always pushing you downwards. The force of gravity is mass times acceleration of gravity. You can write it as F subscript g, or you can write it as m times g. This is the force of gravity. Force of gravity is always pushing you down towards the center of the planet. Now, the force of gravity vector has to be broken up into two components. It has to be broken up into its y component, and it has to be broken up into its x component. Make sure when you draw the y and the x components that you draw the y component perpendicular to the surface, and you draw the x component parallel to the surface. And make sure the x and y make a nice, neat 90-degree angle with each other. Why is this the y and why is this the x component? Because what we've done is we have transitioned from the standard xy coordinate system where the x-axis is parallel to the surface and the y-axis is perpendicular to the surface. What we've done is, now that our surface has gone up, our surface has tilted by an angle theta, we're going to take our xy coordinate system and tilt it also by the same angle theta. So our x-axis is still parallel to the surface and our y-axis is still perpendicular to the surface. So anything that's going to be on our y-axis is going to consider the y component. This is the x component. So this one is called mgy, and this one's called mgx. This vector is mgy, this one's mgx. The force of gravity, the y component, is responsible for generating friction because this is the component of the force of gravity that's pushing the box into the surface. So this is the component that will generate friction because it's pressing the box against the surface. The x component is responsible for pushing the box down the surface. This will cause the box to slide down, and it may generate friction also because friction will be in the opposite direction. How do you calculate your mgy and your mgx? Well, remember, if this is theta, the same theta applies over here, and then you're going to use your trig functions. You're going to say sine theta is opposite mgx over hypotenuse mg. mgx component over mg. You're going to bring your mg over. So force of gravity times sine theta is going to give you your mgx component. Same thing applies for your y component. You can use cosine theta is adjacent, cosine theta, this is your theta, that's your adjacent side, adjacent over hypotenuse. So mg cosine theta gives you your y component. That's how you calculate your x and y components. Now, the normal force in this particular case is going to be equal and opposite to the y component, because it's the y component that's pushing the box into the surface, and if the surface is strong enough, prevents the box from going in this direction, that means the surface is exerting an equal and opposite force. So the normal force in this case is going to be mgy. And that's going to keep the box in equilibrium on our y-axis. So over here, you have an object on an inclined plane. Over here, you have an object on a flat surface. Now, you notice the normal force matches up. So the box is in equilibrium on the y-axis. It's in equilibrium over here also on the y-axis. Sometimes the normal force will change. It won't be the same as the force of gravity, and that's when there is a rope. There is another force, an applied force, that is pulling on the box at an angle theta. So for example, if you attach a rope to your box and you say that there is a rope pulling on the box, Fa, your applied force, is pulling on the box in this direction. It's kind of like a sled. You have a sled, this box is a sled, there's a rope, it's hanging over your shoulder, and you're walking in that direction, and you're pulling on this rope. So that means what you're doing is, you're pulling at an angle theta, which means you're actually pulling to the right, and you're pulling up. You're doing two things. This is going to be your Fax, and this is going to be your Fay component. So what you're doing with the rope is, you're pulling at an angle theta, which means you're pulling to the right and you're pulling up. How do you calculate your Fax and Fay? You calculate it using the same trig functions, and I'll show that to you right here. Sine theta is equals to opposite over hypotenuse, Fay over Fa. So the applied force times sine theta, Fa times sine theta, will give you your y component, and vice versa. If you did cosine theta is adjacent Fax over hypotenuse, so Fax over Fa, your hypotenuse. So Fa, your applied force, times cosine theta will give you your Fax. The important thing to remember here is, how do you calculate the normal force? Well, now what's happening is the force of gravity is pushing the box down into the surface, but part of the rope's force is pulling upwards. So the box isn't pressing against the ground as much as it was before, because now the box is being pulled up. So if the box isn't pressing against the ground as much, that means the ground isn't going to have to exert a normal force as great as it had to in the past. So now the normal force is going to be a little bit weaker. The normal force will be the force of gravity downwards minus the applied force upwards. So it's going to be mg minus Fay. Vice versa, if the rope wasn't a rope and it was a handle, like a lawnmower, and the handle was connected to a lawnmower, and you were not applying a force in that direction, but you were applying a force in this direction, then your Fay would be pointing down, and your Fax would be pointing towards the left. So if you had a situation where instead of Fa pulling upwards at an angle theta, to the right and up, if your Fa was pushing down and left, if it was drawn down and left, then your Fay would be pointing downwards, and your Fax would be pointing towards the left. In that case, the Fay will be pushing down, the force of gravity will be pushing down. The two forces would be causing this box to push down against the ground, and the ground is strong enough to prevent the box from going through this ground. That means the ground is exerting a force upwards to balance the box. Then your normal force would be the force of gravity plus your Fay. But that's only if the Fay is pointing down. And that happens if the applied force, instead of pulling up and to the right, the applied force was drawn down and to the left. It was diagonally pointing in this direction. So that you have to take into account all the forces that are in play to figure out your force, applied force, your force of friction, your normal force, so on and so forth. Your normal force is very important because your normal force is used to calculate the force of friction. Your force of friction is calculated by taking two things into account. It's calculated by taking into account the mu. What is the mu? This is the coefficient of friction. It is a number between 0 and 1. It's a unitless number between 0 and 1. This is the coefficient of friction. It tells you how rough or smooth the surface is. If you're on sandpaper, this number is going to be 0.9. If you are on ice, this number is going to be 0.1. So it's called the coefficient of friction. It's called mu. And it tells you how rough or smooth the surface is. The other thing that you have to take into account to calculate how strong the force of friction will be is the normal force. Because the normal force tells you how much the ground is pressing against the box. You see, if you put an elephant on top of this box, the box is going to press down against the ground with a greater force, and so the ground is going to have to respond by pushing upwards with a greater force to keep the box in equilibrium, to prevent the box from going through the ground. So then if the normal force increases, the force of friction will increase. So the normal force is an integral part of calculating the force of friction. The normal force and the coefficient of friction are both used to calculate the force of friction. And if you have two types of friction, static and kinetic, you have two types of coefficients of friction. You have a static coefficient and you have a kinetic coefficient. And of course, the static coefficient will always be greater than the kinetic coefficient. And these coefficients have already been calculated for you in many scenarios, and they're given in tables. What's the coefficient of friction of a wooden table? What's the static coefficient of friction of a wooden table? What's the kinetic coefficient of friction of a wooden table? What's the static coefficient of friction for ice? What's the kinetic coefficient of friction for ice? So hopefully this review, this quick review of forces on a flat surface, forces on an angle, on an inclined plane, and a discussion of the normal force and the force of friction. Hopefully this is a good introduction for you before you jump into your chapter and you read your chapter and you watch your videos and you come into class and you do your labs and you have your class discussion. Hopefully this will help solidify these concepts.